Now I introduce the actor-critic method. In actor-critic method, actor used to find the policy and the critic used to evaluate the policy. It's different from reinforce with baseline method. Even they have the same similar formulation. In the reinforce with baseline method, this state value function is just used as a baseline to reduce the variance and speed up the learning process. But in the actor-critic method, this state value function used as a baseline, and also we introduce state value function parameters. This is W. So this state value function used to evaluate the policy. That's different from the reinforce with the baseline method. Or in the original formulation, this target is the expected Q function. However, we don't know that true value. So we use the return to replace the true value. For the one-step update, we just use the return, one-step return from t to t plus 1. And then similarly, we use this one-term return as a moving target. Here is the first term is instant reward. Second term is the approximation for the truncation. And this is the state value function used as the critic right now. And this is the policy gradient and divided by the policy. So we further use this delta to represent this error, or this called TD error. And then we use this actor to update the policy parameters theta. And in the critic, we use this W to update the state value function. Use this way, we finally get the convergent state, convergent policy parameters, and then use this theta to calculate the optimal policy, and then to estimate the optimal state value function and the action state value function. For one step TD, that means TD0, we use the Salmon gradient method. So the Salmon gradient method, that means when we calculate the gradient of this increment with respect to the parameters W, we only consider the second part. When we ignore this part, that means we calculate the derivative of this delta. We only, we only consider this part. We will suppose this part is no relation with the wave vector W. So to do the one-step actor-critic method, we are first for one episode. One episode, then we start from the initial state S, then we'll select action and the policy pi. By taking this action A, we receive reward, and we observe the next state. And then we calculate this delta is a TD error as a moving target, and this is a state value function. And then we update the W for the state value function by using the Salmon gradient, and then we update the policy parameter theta in the this way using the policy gradient, and then the agent moves from state S to next state S prime. Then we go on next cycle step by step. Finally, we reach the convergence state W and theta. From convergence theta, we can calculate the optimal policy, and then to estimate the optimal state value function and the action state value function. It's easy for us to extend the one-step actor-critic method to n-step or the lambda return method. Just replace this return, one-step return, with this n-step return or with the lambda return. Here, the eligibility traces are used in both actor and critic. Here, this is eligibility vector. So the procedure is similar to the one-step actor-critic method. We start from one episode, select initial state and initialize these parameters, and select action A and the policy pi. We observe this next state S prime. We receive this instant reward, and we calculate, use this moving target and the state value function. We calculate this delta, and then now we update this eligibility for the state value function and for the policy. Here we use the semi-gradient method to update this eligible vector for the state value function, and then we update the wave vector W and wave vector theta, and then the agent moves from current state S to next state S prime. So on next cycle, step by step until we reach the convergence W and theta. Once we have this theta and W, we can calculate the optimal policy and estimate the state value function and the action state value function. For more details, please check with this reference. Thank you. Bye.